answer will be, say, tau. So we have only one component of shear stress. I want to see what will be the yield stress when you do a simple shear test. So what is the relationship between yield stress in shear and the yield stress in tension? In tension, we found that J2 is equal to sigma y. But in shear, let's see what happens. So in the shear, then, there is no deviatoric, there is no trace of diagonal components. So this is also S. Deviatoric stress is the same. So if you take square of this, that should be 0, tau square 0, tau square. No. So Sij should be S12, twice of S12 square. There's only S12 is the only one non-zero component. So now you can see that, so my sigma y, if I plug in there, it is 3/2 times twice S12 square root will be my, so the yield stress in tension is square root of 3 times yield stress in shear. So that's the relationship between the two. So if you do a shear test and find the yield stress, square root of 3 times that will be the yield stress in tension. Does it make sense? Okay, now let's go and solve a problem for a thermo-viscoelastoplastic material. I'm going to do a one-dimensional problem. I think some of you are still looking at there. Does it make sense, what I did? Okay, so let's look at the torsion problem. So this is my thin tube. So we apply torque on one end and the opposite on the other end. So it's equilibrium, or at least if you are not applying a torque here, you are holding it fixed. And we could be twisting at a high strain rate, right? Very rapid twisting. So let's look at this small portion. Strain rate can be 10,000 per second, million per second, doesn't matter. So it's not something like 0.0001 second. It can be that too, it's no problem. So the strain rate is not a grid. We will consider inertia forces. So strain rate is not a, so long as we have material properties, it doesn't matter. Okay, so if you look at this small piece, this thing seems to be moving that way relatively, and then this one is going down. We are going to look at a very small piece. So my window is on the top surface is something like this. So I'm just looking at a small piece element. And now I should draw the free body diagram of that small piece. Also, I'm going to, so that small piece is going this way and that, and if you say it's a shear stress, we must have shear stress on the top and the bottom surface. It's anti-symmetric about this axis. Like this thing is going up and that one is coming. So it's anti-symmetric or skew. Now let me, just for my own thinking or view, let me rotate it through 90 degrees. But it doesn't change the problem. So I'm going to rotate it through 90 degrees and look at this piece. So this axis of symmetry is this one, and I'm going to do half of the problem. So if this thing is moving up and that is down, so the mid part is at rest, stationary. And I've turned it, say, maybe more than 90 degrees or 270 degrees. So I'm going to say this thing is going to the right. But it's a rigid body rotation, so it doesn't change anything. So now let's choose the coordinate axis. So we have x-axis this way, y that way, and basically what I have is a simple shear problem. And these ends, you can say, is they go forever. Things vary only in the y direction. So it's a one-dimensional problem. And there's only one component of stress, that is this S, called tau. And I wrote there tau. So shear stress. So let's say, and we can say either the shear stress is prescribed on the top surface or the velocity is prescribed on the top surface. So we are going to say velocity is prescribed on the top surface as V bar. Now we need to write the equation of motion. You see, it looks like, so if you take a small piece, no, it's a smaller piece than the one we considered there. And so we see that there is a tau plus delta tau times area. So if this is delta x, dimension perpendicular to the screen is 1 or b, so that will be b times delta x. Here it will be tau plus tau b delta x, and equation of motion will be then force in the x direction. So that's tau plus delta tau b delta x minus tau b delta x equal mass times acceleration. So mass is rho b delta x times delta y. That's this dimension is delta y times acceleration. So that's delta v over delta t. Rate of change of velocity. And this is the material description. Like even though I'm using little x, material particles, are not changing. So little x is my, I think yesterday or day before. All these particles, they are moving parallel to the horizontal axis. Does it make sense or not? So what I get then is rho delta v over delta t equals delta tau over delta y. Because you can see b delta x cancels from everywhere, divide by delta y, take the limit as delta y goes to 0. So this is the equation of motion. We need to express for tau, like in the linear elastic case, we said tau is equal to, if this is a shear modulus times the shear strain. But this is not a small deformation problem. This is not a small deformation problem. Also, there is a temperature change. Because we talked about that when you deform a body plastically, there is a temperature change. So let's write the energy balance. What is the, if E is the specific internal energy, then rho times delta x b times delta y. So this is the mass, and that's the mass density. I said specific means internal energy per unit mass. So it's E dot, that's the rate of change of internal energy, multiplied by the mass, so that's the total rate of change of internal energy. So that should equal the work done by external forces, which is tau plus delta tau times b delta x times v plus delta v. If the velocity at the top is v plus delta v, minus at the bottom rho b delta x times v. This velocity, in both cases, particles are moving to the right. So in this case, the particles are moving this way. In this case, also the particles are moving this way. So they are doing positive work, they are doing negative work. Does it make sense? What else can be there? What other term should we consider? Pardon? Yeah, but that is included E. E is internal energy, so that includes the energy due to deformation. No? You're right, so we can take kinetic plus, say, 1/2 rho delta x b v square times dot. So rate of change of internal energy plus rate of change of kinetic energy equals that. So what else should come into picture? Hint. We did that on the very first day of the course. Pardon me? Wait, just 1%. Yes, sir?
Source.
Yes, we had its external source. Let's assume external source is not there. You guys are talking with each other, so what is your opinion? Collective opinion. Yes, sir? Now, remember, we started this class on Monday, 19th of this month. It's only 10 days ago. So what was the first differential equation we talked about? Conduction, heat. So there is heat. Have we ever talked about friction yet? So I was trying to remind you of the very first day. So we talked about heat conduction. So that's what we need. Not source term. Source, somebody already said. Conduction. So what is happening is this one is giving heat going out, maybe delta Q times area. So it's B delta X. And here we have again Q, B delta X. I think now in one side it's coming in and going out. So we had something like this. And so what will happen is then you have Q delta O. My sign is not coming out right. Okay, so we had Q plus delta Q times B delta X minus Q B delta X. And plus, if you have a radiation term, you will include that, but normally in In mechanical problems, we don't include it. The reason I included it on the very first day was to, well, basically to make the problem non-homogeneous. So you had a source cell. Otherwise, it would have been like temperature would have been d2 over dx square equal to 0. That would have been the equation. Because we did steady state heat conduction. And if there were no source, it would have been d2 rate of second derivative of the temperature with respect to x equal to 0. And that would have been less interesting than if we had the R term. But normally we don't include that R term, source term. Okay, somebody said viscous, that will become, because the tau, the shear stress depends upon strain rate. That's how the viscous dissipation will come into picture. This stress, we are doing plasticity, so there will be some energy dissipated. So that will come into picture through tau. So there is no external source that we are considering. There is no radiation term. So it's only heat conduction because this thing is touching the next particle to it, and there is work done by the internal stresses. Okay? So let's try to simplify this. So we have rho E dot plus 1/2 rho V dot. There is no 1/2 here because when I take V square, so it's going to be twice of V dot. And we are going to divide by B delta X everywhere. Oh. So I think I forgot delta Y here because it's mass times kinetic energy, mass times V square. So I forgot delta Y here. Sorry. Otherwise, it would not have been mass. So we are dividing by B delta X delta Y everywhere. We need 3 dimensions to get volume. So delta X, B, and delta Y. Okay, now on this side. So we have, I should be careful, we have tau V plus tau delta V plus delta tau delta V plus delta tau V. 4 taus. And then we have here minus tau. All of it multiplied with V. V delta X we are going to divide by. So we divide by delta Y also then here, because we divided by rho delta X B times delta Y. Is it okay? And when we come here, so we are dividing by this, so we have Q plus delta Q minus Q over delta Y, and there's a plus sign. So that's the balance of energy, balance of total energy. So that's rate of change of internal energy plus rate of change of kinetic energy equals the work done by forces on this element now. So on this element, you have this stress and that stress. You multiply by areas, you will get forces. Multiply by velocities, so that will give you rate of work done. And then you consider the heat conduction part. Okay, so let's take the limit as delta Y goes to 0. So we have, कौन सी convection? कोई air नहीं blow कर दे. But that, if you want to consider convection, that comes on the boundary terms. That comes on the boundary condition, not here. This element is inside the body. Okay, so if we do this, so tau times V, there should have been tau. This should have been, parenthesis should have been here, not, V was not outside, because this is tau V, delta V, so this V was not outside. So this term will cancel with that. So what we get then is tau delta V over delta Y plus, this is second order, so we don't consider it, and that's V delta tau over delta y plus delta q over delta y. Sorry, just 1 second. This sign is wrong because this is heat going out, that's coming in. This is going out, that's coming in. So I'm sorry. This is second derivative. Sorry, this is second order term. Say if I say is delta tau over delta y, then this thing will go to 0. If I say this one, then this will go to 0 in the limit when delta v goes to 0. So this term is not contributing because this is a second order term. That's why when you take the limit, this goes to 0 faster than this one. Okay? Pardon me? Why? This is coming in, that's going out. It's a one-dimensional problem. It's a one-dimensional. Only one-dimensional problem. Things are changing only in the y direction. Okay. So if we take this, so we can say rho delta E over all. I have not done that part yet, so let me not say anything. But let's look at this. So we have this rho v dot, because delta v over delta t is v dot, right? So we have rho v dot. So this thing gives me rho v dot equal to v delta tau over delta y. Multiply both sides by v. That thing says that this term should cancel with this one. Right? See, we agreed on that one. That was balance of linear momentum or mass times acceleration equal to the force. Multiply by both sides by v. So you get rho v dot, and that's v over delta t over delta t. So that this thing is equal to that. So that cancels from both sides. Is it okay or नहीं आप कुछ नहीं हो? I mean, I can take this term to the left-hand side and say it's rho v dot minus delta t over delta y multiplied by v, but that is 0. Okay, so now, so we have the second equation. So we have rho E dot equal to minus delta q over delta y plus tau delta v over delta y. We are not done yet because we have, how many unknowns we have here? So we have, if you count the unknowns, we have v is unknown, tau is unknown, E is unknown, Q is unknown. So we cannot solve the problem. We have only 2 equations, plus we have not talked about the material yet. We have not said this body is made of copper or steel, except through the mass density. The only term that is material dependent so far is mass density. Okay, so now we say gamma, this is shear strain rate. Delta v over delta y is shear strain rate because this is a rate of change of velocity, not displacement with respect to y. So let's call it gamma dot. So that's delta v over delta y. So we introduce one more variable. So this is So in plasticity, we assume that strain rate has additive decomposition, not strain. We don't assume, unless you are doing a small strain problem, we do not say strain equals elastic strain plus plastic strain, because these are components. But strain rates you can say. Strain rates, whether you take scalar, like I have only one component, or kursi upar karo, no. Nahin? Idhar aa jaao. Come in the front, because you are having difficulty seeing it. Sorry to make you move, but there's a chair there, or you can pull that chair here. So this, we assume that in plasticity, the strain rate equals the sum of the elastic part plus sum of the plastic part, not strains, unless you are talking about small strains. For small strains, yes, we assume that. Otherwise, we say deformation gradient is a multiple of, is a product of elastic part and plastic part. So that's matrix multiplication. Of which order? I think it's FE, FP. F elastic, then multiply by F plastic. But in my work, or in the work of my group, we have been using this. So whether this is a, if it is a three-dimensional problem, then we will write Dij, which is a strain rate tensor we introduced before lunch, equals Dij elastic plus Dij plastic. आपका स्टूडेंट नहीं आया? Oh, better. No, the one who showed me paper, he needs this stuff. But it's up to him, and it's okay. He needs it, but it's up to him whether he wants to come or not. Okay, so we assume that the strain rate is the sum of the elastic part plus the plastic part. Pardon me? Rational, is the assumption hai. All I'm doing is saying 5 equals 3 plus 2. Nothing wrong with that. All we are saying is 5 equals 3 plus 2 or 4 plus 1. So it's, we have not done anything. There's no, this is not any assumption. We are just writing it in sum of two parts. Okay, in plasticity now, we need to write the constitutive equation here. So the stress evolution depends only upon the elastic strains, because you are required to stay on the yield surface. So you can only, in this case, the yield surface is basically tau y equal to some constant, if my yield surface is not expanding or shrinking. So I'm always supposed to stay on my yield surface. So the evolution of stress is only due to the elastic deformations. So I need now here constitutive relation. So my S dot is equal to twice mu of gamma E dot. So now how do I find gamma P dot? And once I can find gamma P dot, then I will have more, well, not quite yet, because I still have Q to worry about. Q is simple. Fourier's law of heat conduction. We studied that before also, like Fourier laws of heat conduction. So that's Q equal to minus K delta theta, which is temperature over Y. You can have K depending upon temperature, or you can have K constant. Or you can have K depending upon plastic strains. I mean, it's possible. But theory doesn't rule it out. The thermal conductivity can be constant, can be temperature dependent, can be strain dependent, can be strain rate dependent. Don't ask me what are the expressions, but in principle, yes, you need to do experiments to figure it out. But nothing. So we still have a problem because we don't know what is gamma p dot. So in the morning we said that the yield stress, if you remember, I drew those stress strain curves, and I said if the strain rate is increasing, the flow stress or the yield stress is increasing, and if the temperature is increasing, it is decreasing. So let's say my yield stress then is some constant. It's a function of temperature, it's a function of plastic strain, and it's a function of plastic strain rate. I'm not giving you the functions, but these functions, they depend upon the material, like what function you should take. Commonly used is Johnson-Cook, or Borden-Parton, Armstrong's Rayleigh, Littonsky. There are many of them in the literature. So which one to use is your choice. There is no implication that the results you will get will be independent of your choice of these functions. So tau 0 has the units of stress, and the remaining are basically non-dimensional. So these functions, the forms of these functions determine how rapidly or how slowly the material is hardening and softening. These multiplication, assuming that they are multiples of functions of temperature and strain rate, is an assumption. I mean, real life, nobody knows how the materials behave when you change the temperature, strain, and strain rate, because as soon as you deform something plastically, its temperature changes. And nowadays we have instruments like infrared thermometers that can determine or detect the temperature locally at a point in time. If you go to Beijing, China, before you even enter the immigration, they take your temperature. They have an infrared camera at the airport. As soon as you come out of the airplane, you go through some walkway. Before you go to the immigration port, they take temperature. The thermometer takes temperature, and if your temperature is not normal, they pull you out, and you cannot enter the country. You cannot enter Beijing, which is good. I mean, they don't want any sick people to get in. I'm not kidding. I have gone there, so I know. I have not been picked up and said, hey, you have a fever, but the whole purpose of that thermometer is to find out if somebody has fever or not. Which is good. I mean, it's not, there's nothing wrong with it. So the point is that there is an infrared thermometer that you don't have to put in your mouth to take the temperature. So it really takes the temperature of your forehead. And same thing on my specimen here, if I can focus my infrared camera and take the temperature of these particles as it is deforming. Also, if I can take pictures at million frames per second, that means every microsecond I know what is the strain and what is this, then I can find the strain rate also. So now there is sophisticated stuff. This is expensive, of course, but we saw very expensive AFM, atomic force microscopes at MIT. So people can afford it. Okay, so now I'm going to assume that I can solve this equation for gamma p dot. So gamma p dot, I can solve this I'm trying to think of some, like FGH, I should not take I, J, K, L, M, N, those are generally integers, PQR, so let's say R. So it's a function of theta and my shear stress and strain rate, no, strain. So I can solve this equation So if my shear stress, if my stress here, this tau, satisfies the yield criteria, I will solve this equation for this. Otherwise, it is zero. There is no plastic deformation. So if my stress is less than the yield stress, there is no plastic deformation. If my stress equals the yield stress, I will solve this equation for plastic strain rate. So my equation here then becomes gamma p dot is equal to maximum of 0 or this value. And this is 0 if tau y is less than the yield stress. Basically, if I say, maybe I should like, if tau minus tau 0, f, g, and h is less than 0, then my gamma p dot is 0. That means there is no plastic strain. Plastic strain rate. There is no plastic deformation in the next time increment. And if this equals 0 or greater than 0, then you solve this equation to find for gamma p dot. Now I think you asked me why did we do this? 4 equal to 3 plus 2. You are finding 2 here, right? This quantity you will find when you will solve for velocity. Therefore, you can find this. Because we are going to eventually solve for velocity. Our equations we are going to do, we are going to solve them for velocity and temperature. But I have not given you the equation for temperature yet. I'm coming there. Any questions up to this point? None. Okay. So E dot, which we have not talked about much, this E dot is delta E over delta theta, which is temperature times temperature dot plus delta E over delta gamma elastic dot and this tau delta V over delta Y is tau gamma elastic dot plus tau gamma plastic dot. Is it okay? I'm assuming that my elastic, the energy, internal energy E stored in the body is because of the temperature rise and because of the elastic deformations. Because of the plastic deformation, that energy is dissipated. That is not stored in the body. So the recoverable part is due to elastic deformations. And then I'm not saying this is the recoverable part, but the internal energy can increase because we are increasing the temperature of the body. So this thing is generally called specific heat, C. This thing is generally called specific heat, and this quantity equals that. The work done by internal stresses to deform the body elastically, that is stored in the body. That's recoverable. So this term equals that. This is specific heat, and therefore my energy equation becomes rho C theta dot equal to minus delta over delta y times k delta theta over delta y plus tau gamma p dot. Oh, sorry, okay. Oh, sorry, yeah, okay. I should have. So now we have this internal energy equation. I have combined this with that, and I have combined this term. So it rate of change of temperature, this is specific heat. So this term is the one that plastic working, the working means rate of work done by internal stresses to deform the body plastically, that is generating heat, that is serving as a source of heat, and thus raising the temperature of the body. So if the body is deforming elastically, this term is 0. If it is deforming plastically, this term is positive, and there is heat produced or heat generated in the body, and that's what causes the temperature to go up. Now if you count the number of equations, so let me rewrite it. So we have rho v dot equal to delta tau over delta y, then this, and we have gamma dot equal to delta r. We have gamma dot elastic is equal to delta v over delta y minus gamma dot plastic, and we have s dot tau dot, sorry, I have written there s tau dot equals twice mu gamma e dot, and we have gamma p dot is either 0 if my tau is less than the yield stress, and it is the solution of that equation. So this tau gamma p dot, gamma p, sorry, it's either that or this, depending upon if my tau is greater than or equal to the yield stress. When I write here yield stress, this yield stress is a function of temperature, strain rate, strain, and no, strain rate I'm solving for. Yeah, it's a function of strain rate. So this is not yield stress, is not like you get from a static test. This is different at different points in the body. So basically what you do is you find these yield stress at the previous time step and use it for the current time step to check if the material is going to deform elastically or plastically, and then you do one more iteration within the same time step before you march forward, before you go further in time. Okay, now let's see if we have the right number of equations and the number of unknowns. So our unknowns here are V. We will solve for V, we will solve for theta, we will solve for gamma p dot or gamma, and then you have tau dot. So you have 4 unknowns, 1, 2, we don't count this, we have 3 and 4. So we have right number of unknowns and the right number of equations. All we need is initial condition and the boundary conditions. These are highly nonlinear equations. These are highly nonlinear because this thing is highly nonlinear. The dependence of the yield stress upon temperature and strain rate is highly nonlinear. Okay? So because of that nonlinearity, it's affecting everything. That nonlinearity is causing problem here. Because tau is nonlinear, function of temperature, plastic strain and plastic strain rate. This is again another plastic strain rate term here. Temperature you are trying to find from here. So this temperature is a function of the plastic working. So everything is coupled together. So if the temperature at any point is higher than the temperature at the surroundings, the flow stress or the yield stress or the stress required to deform it plastically will be lower. Which means if you are applying a tangential load or the shear stress, that material point is going to deform rapidly. And if it deforms rapidly, it will produce more, there will be more heat produced locally. That means it will become softer. And then next time it will deform even quicker. So it's a self-feeding phenomenon. You know where I'm getting at? If you have a small defect, which becomes locally heated somehow, then just plastic deformation near that point will become very large. You cannot avoid it. Because the material is thermally softening. So there will be an instability occurring when the material can no longer support this load you are applying or the local stresses. So the strain rate locally will start becoming very large, and you will see what you may call shear band, because locally the deformation will be very large. Finding the width of that region is a challenge, because the width of that region that has experimentally is something like 30 or 40 microns. 1 micron is 10 to the minus 6 meters. The thickness of a human hair is of the order of 80 microns or so. On the average, I'm not saying you are on mine, but on the average it's something like 80 microns. So these shear bands you see in experiments, it occurs in penetration problems. Whenever you have high strain rate loading, it occurs in earthquake loading, it occurs in machining, it occurs in ore crushing, and this is a very serious failure mechanism. So many metals fail because of the initiation and propagation of the shear bands, or these small regions of large plastic deformation. Okay, so if you want to solve the problem numerically, the next step is get a weak formulation of the problem. And that you know by now, right? So get a weak formulation of the problem, and you need initial and boundary conditions. Initial conditions are at the lower surface, velocity is given, and at the top surface, you prescribe velocity as a function of time. Generally, if you prescribe load as a function of time, then it becomes harder to solve, because eventually the load starts decreasing as the time is increasing, and there is no mechanism for us to decrease the load, because we cannot predict beforehand what the load should be. So the problems we solve, we prescribe the velocity here as a function of time on the top surface. Heat flux, if you are interested in convection, then you will prescribe the boundary condition here for convective heat transfer, which means the heat flux will vary with the local temperature, and depending upon the airflow, that can be temperature raised to the power 4 minus the ambient temperature raised to the power 4, or temperature raised to the power 2, I don't know. Depending upon the convective heat transfer law, you will have that. Then you need convective heat transfer coefficient. That will depend upon the velocity of the air you are flowing over it. So there are many factors involved. The simplest is, of course, you assume there is no heat flux going out from there, and there is no heat flux going out from here. And that way, all of the heat produced in the body is retained in the body. But it's your choice. It's your choice of the boundary conditions. You have to look at the experiments, where the experiments were done. Now, typically, these things happen in a millisecond, which means if you blink your eyes, it's too late. It takes you a little more than, maybe it takes you a millisecond to blink your eye, and these things are gone in a millisecond. So try how many times you can blink your eye in a minute, then you can see what the time period for the blinking of the eye. And if you blink your eye, you have not seen the experiment. If the strain rates are if you apply a strain rate of say 1000 per second, which is very typical, this is nothing 1000 per second, locally the strain rate can be million per second, wherever the defect is. So locally the strain rate can be very high, and that's where the failure will occur. All you need is one inhomogeneity in the body. If the body is isotropic, well, isotropic doesn't make any difference here, but if the body is homogeneous, no defects, then you will not get any instability, unless your numerical algorithm introduces a so-called defect in the solution or perturbation in the solution. Except for numerical errors, then you will not get any instability. So you have to introduce a defect or some kind of perturbation. Is similar to sometimes when we study buckling, that if you don't introduce any defect, you don't see buckling. Same thing here. So you have to introduce defect. Depending upon where you introduce defect, how big a defect you introduce, the instability or the shear band will occur at different times. You can introduce multiple defects, say I'm going to have a defect here, defect here, defect here, a defect here, and then see how these defects will interact with each other. There is no guarantee that if you have introduced 4 defects, you will get 4 shear bands. You may get only 1, or you may get 2. There is no length scale in the problem. This is local theory. There is no gradient type theory. If you like, we can introduce gradient type theory too, but then you have to solve for one more variable. Okay, so I think I have spoken enough. So any questions? Mechanism, okay. Supposing I have a defect here. Defect means this material is a little bit weaker than the rest of it. Okay? So when I deform it, initially stress is uniform everywhere. This material is weaker, that means it will start yielding first. So if it starts yielding first, plastic strain here will start going up first. So if the plastic strain rate starts going up first, there is going to be more heat produced at that point first. More heat produced, more temperature rise, becomes even softer, which means deform even faster. But this term dominates the other one. Yeah, initially yes, the band will initiate only when, if you are on this stress strain curve, so only if you have crossed this point. It will not initiate it whenever you are here. Actually, it does not initiate there also. It initiates when you are somewhere here. You are beyond that maximum in the stress curve. How far beyond you have to go, I give you the answer. So once you are there and it starts rapidly deforming, only God can save you. There is no way, even if you unload it, there is very little chance that you will recover the sample intact. Remember, no, this is a simple shear problem. But if you do a complex loading problem, then things are different. Because in this case, there is really not much, because it is shearing this way, once it starts sliding, there is not much to prevent it from going faster and faster. But if you are doing a, say, 3-dimensional problem, then if there's a locally inside some defect or softening, there's a lot of material around it that can prevent it from propagating throughout the structure. So 3-dimensional problems, there are no, whatever I'm saying, you have to take with a grain of salt. Physics remains the same, but you can still prevent it. Even if the local instability occurs, the structure is not gone. In this case, it is gone, because when you are twisting it, once it starts twisting faster, then you cannot save that cross section, which means it will just break. But in 2 or 3-dimensional problems like penetration problems or, well, basically penetration problems. Either you do Taylor impact tests or you do a missile going into a tank wall, or you have a missile going into, say, underground shelters. In those cases, there is no guarantee that once one shear band forms, you are done. No, there you have to do, it takes a lot more effort. It's very small. You have to do numerical experiments to find out. I cannot tell you in advance. It generally depends upon thermal conductivity. Okay, many people, because that is the only thing that introduces a length scale into the problem. But it's a very weak length scale. So thermal conductivity, if you do not consider thermal conductivity and do not consider a gradient type theory, strain gradient type theory, there is no length scale in the problem. So thermal conductivity is the only one in this case that helps. But it's a very weak dependence. If you refine the mesh and have no thermal conductivity, the bandwidth will keep on getting smaller and smaller and smaller. And eventually we have to stop the computation anyway. So these computations are expensive. Expensive means they take CPU time. It's not a joke. The time step size is of the order of 10 to the minus 9 or 10 seconds, or maybe smaller, which is the same thing happens in MD simulations, so don't get surprised. In molecular dynamic simulations, time step is of the size of femtosecond, that's 10 to the minus 12 seconds. So if you are doing MD simulation and you can do for, say, 100 nanoseconds, that's great. Nanosecond, that's 10 to the 100 nanoseconds means 10 to the minus 7 seconds. So that is, you can blink your eyes many times in that. Actually, you cannot blink your eye any time, sorry, I said it wrong. Yeah. Sure, but try to make the material homogeneous. Only God can help you. There is no material in the world perfect. So making it homogeneous, you can spend crores and crores of rupees. Maybe you can make one sample. See, you cannot make it homogeneous. Yeah. No, you cannot. That's the way life is. Actually, non-homogeneous materials many times are stronger than homogeneous materials. See your own body. It's highly heterogeneous. You have bones, you have skin, you have nerves, you have soft tissue, and blah, blah, blah. Everything is anisotropic. My bones are not isotropic, neither are your bones. So nature has designed things optimally, and that optimal design requires that structures be non-homogeneous and possibly anisotropic. This only gives you the framework, it does not solve problems. No, it's not necessary to assume that material is homogeneous. Here we did not accept for, actually in this case we have not assumed the material is homogeneous. I still have K inside, the derivative sign. So there is nowhere there is the assumption of material being homogeneous. Pardon? Your dam is not homogeneous. You go and see dam. They look at the building structure. You have a concrete, you have a brick, then you put mortar, then you put another brick. Okay. You make piles, civil engineering, right? Piles. They are not homogeneous. You have a reinforcing steel bar. Oh, calculation. Yeah, calculation purpose. 99% of the time we also do the same. But that's a different story from doing real, like when they design tank walls, they don't assume that. When we design missiles, we don't assume that. But I have never designed a missile, I have never designed a tank wall. So don't think that I have done any of that work, but these things are applicable there. But these things are not applicable to design my shoe. Nobody is going to pay me to do this kind of work. Hey, Nike is going to kill me. Hey, you are going to take 10 days to design my shoe? Forget it. Actually, they should pay us to design the glue, because sometimes the sole comes off. And then but they don't pay you for designing even the adhesive. They do a test, I think. Okay. Good luck with if you want to pursue this. Pardon? It depends upon the strain rate. It can be materials can melt. Yeah, they can melt. Pardon? It depends upon the material. I mean, I cannot tell you different materials melt at different temperatures. Talk to them. They know lot more than I do, but they cannot probably talk to you. See, the problem is these things are based on your need to know, and you don't need to know this, so we cannot talk to you about it. Neither they, well, I can, because I have not worked on any of these kind of problems, like real problems, but they cannot talk to you, because you don't need to know that piece of information. And similarly with me, I don't need to know it, so I don't know anything in real life when they design what is the temperature, blah, blah. I do not know. I cannot ask that question. I'm not authorized to ask that question. In the class, you can ask me, but I'm not authorized to ask in real life. Even if I talk to them, I am not allowed to ask. Because if I ask, that will tell me, show me your ID, show me that you have security clearance. Don't. Okay, thank you. I think we are right about on time for the tea break. Just 5 minutes over. Sorry, but just about on time. And I'm not going to talk after the tea break.